sklearnmetricslabelrankingloss. Description: the label ranking loss function calculates the average number of label pairs that are incorrectly ordered, based on the predicted scores and true labels. This metric evaluates the performance of a ranking model, where the goal is to rank the labels in decreasing order of their relevance. Inputs: Y true. This is a 2D array representing the true labels. Each row corresponds to a sample, and each column corresponds to a label. The values in the array should be binary 0 or 1, indicating whether the label is present or absent for that sample. Y score: this is a 2D array representing the predicted scores for each label. Each row corresponds to a sample, and each column corresponds to a label. The scores should be real valued, representing the model's confidence in the presence of each label. Outputs: label ranking loss. This is a single floating point value representing the average number of label pairs that are incorrectly ordered. A lower value indicates better ranking performance. Steps: for each sample, calculate the number of label pairs that are incorrectly ordered based on the predicted scores. Sum the number of incorrectly ordered pairs across all samples. Divide the total number of incorrectly ordered pairs by the number of samples to get the average. Label ranking loss. Metrics: mean average precision map. This metric measures the average precision of the model over all samples. It is a common metric for evaluating ranking models. Normalized discounted cumulative gain (NDCG). This metric considers the position of relevant labels in the ranking, giving higher scores to models that rank relevant labels higher. Visualization plots. Receiver operating characteristic (ROC) curve. This plot can be used to visualize the trade-off between the true positive rate and false positive rate at different thresholds. Precision recall curve. This plot shows the relationship between precision and recall at different thresholds. Fine-tune parameters. Regularization parameters. These parameters can be used to control the complexity of the model, which can help to improve generalization performance. Learning rate. This parameter controls the step size taken during optimization. A lower learning rate can lead to more accurate models but can also slow down training. Uncertainty methods. Confidence intervals. These can be used to quantify the uncertainty in the model's predictions. Bayesian methods. These can be used to incorporate prior knowledge about the problem into a model. Challenges and fixes. Challenge 1: imbalanced data. If the data is imbalanced, i.e., some labels are much more frequent than others, the model may be biased towards predicting the more frequent labels. Sample use case that resulted in challenge 1: a dataset with 90 positive labels for label A and 10 positive labels for label B. The model may always predict label A, even when label B is more relevant. Fixes to challenge 1: use techniques like oversampling, undersampling, or weighted sampling to balance the dataset. Challenge 2: multicollinearity. If there are strong correlations between the features, the model may have difficulty learning the relationships between the labels and the features. Sample use case that resulted in challenge 2: a dataset with 2 features, both of which are highly correlated with label A. The model may not be able to determine which feature is more important for predicting label A. Fixes to challenge 2: use feature selection methods to remove highly correlated features, or use regularization techniques to penalize models that are too complex.